Okay, we come to esters. They have the general formula RCOOR dash, and we'll look at a picture of one soon. Actually, let's look at a picture now. Ignore the stuff about the naming for now. We'll come back to that. But this is an ester called Ethyl Propanoate. So can you see here that this is the propanoate ion? So it's like propanoic acid minus the hydrogen. So that's our propanoate, and then attached to that from the oxygen we've got an ethyl group. Excuse me. So we call this ethyl propanoate. That's an example of an ester. Note the fact that it has two alkyl chains. One chain here attached to the oxygen, and another chain here attached to the carbonyl carbon. So the naming is something ill, something anoate. We looked at a previous example was ethyl propanoate. The way we name it is we divide the ester into two groups. In fact, I'll just walk through it here. So in this case, we draw a line. We look for the carbon that has the double bond to the oxygen. That carbon will also have another oxygen attached to it. We draw a line after that oxygen. And then the naming is firstly whatever group this is, so methyl or ethyl or propyl or butyl or whatever. And then we've got our carboxylate ion, in this case propanoate. So the naming is ethyl propanoate. The other way around, again we look for our carbonyl carbon with the oxygen attached, draw a line after that oxygen. That leaves us with ethyl over here and propanoate over here, ethyl propanoate. Esters are colorless liquids. They have no hydrogen bonding and they're more volatile than alcohols or carboxylic acids. They're not very soluble in water because they're largely non-polar. They have low boiling points because of the weak intermolecular forces between the molecules. And important or common uses of esters include perfumes, fruit flavorings. They have smells like flowers, fruits, and perfume sort of smells. That's what esters are often used for. Okay, we're going to look at reactions including preparation, hydrolysis, reaction with ammonia or amines, and soap making. So how do we make an ester? Well, two ways. We can react a carboxylic acid with an alcohol, or we can react an acid chloride with an alcohol. Either of these will produce an ester. The way, so we're going to look at an example on the next slide. If we start with a carboxylic acid, we get water as a byproduct. If we start with an acid chloride, we get hydrochloric acid as a byproduct. So let's have a look at an example. Let's take ethanoic acid and ethanol. Now, the ethanoic acid part becomes the carboxylate. The carboxylic acid part becomes the carboxylate part of the ester. So in this case, ethanoic acid becomes the ethanoate. So that's over here. This is our ethanoate. No, sorry. This is our ethanoate. Our ethanoate is this part here. And then the alcohol produces the alkyl group that we start the naming with. So in this case, we've got ethanol, so we get ethyl, and this is our ethyl over here. So we've got ethyl, ethanoate, the ethyl coming from the alcohol, and the ethanoate coming from the carboxylic acid. Similarly here, we take ethanol chloride and react with propan-1-ol. It must be a primary alcohol that we're using in the reaction. So again, the ethanol chloride part becomes the carboxylate ion part. So we get from ethanol chloride, we get our ethanoate, which is this part here, our ethanoate, and the alcohol contributes the alkyl group, which we begin the name with. So in this case, propyl. So this is our propyl group, which comes from the propan-1-ol from the alcohol. So propyl ethanoate, the ethanoate coming from the acid chloride, and the propyl coming from the alcohol. Okay, the reaction between a carboxylic acid and an alcohol to produce an ester is a pretty slow reaction, so we generally speed it up by performing the reaction under reflux. and adding a catalyst such as sulfuric acid. So just a reminder of what reflux is. It's a way of adding heat without losing our reactants, because as we add heat, as we said earlier, esters have a relatively low boiling point. So the problem with adding heat is that it speeds up the reaction, but it also makes the ester boil as it's produced. So to avoid losing the ester, what we do is we add heat and sure the ester boils, but then we cool this tube by circulating water around it, and then as because this part is cooler, as the ester rises, it condenses and comes back into this container, so we don't lose the ester as we're making it. The reaction between an acid chloride and the alcohol is fast and vigorous, and this is because acid chlorides are highly reactive, so we don't need heat or a catalyst, which is why it's a preferred method of forming an ester. Okay, hydrolysis, the reaction of an ester with water, can be carried out in either acidic or alkaline conditions. If we look firstly at acidic conditions, what happens is it splits. In acidic conditions, it splits the ester back into its carboxylic acid and alcohol. So just as we form an ester by reacting a carboxylic acid with an alcohol, if we hydrolyze an ester in acidic conditions, we go back to a carboxylic acid and an alcohol. So again, the propanoate part becomes the carboxylic acid. So from propanoate here, we get our propanoic acid, and the ethyl part becomes our alcohol, ethanol. That's our ethyl part here becoming our alcohol. It's just a reversal of the reaction when we produce an ester by reacting a carboxylic acid with an alcohol. Okay, here it's shown here diagrammatically. So this is our propanoate. Our propanoate becomes propanoic acid, and our ethyl becomes ethanol. Okay, in alkaline conditions, we're reacting basically with hydroxide ions. We get a carboxylate ion and alcohol, so the alcohol part is the same, whether it's in acidic conditions or alkaline conditions. But instead of getting a carboxylic acid, we get a carboxylate ion, and that's easy to see where it comes from. We get the propanoate ion. Obviously, it comes from the propanoate part of the ester, which is this part here. And again, the ethyl part becomes the alcohol, in this case ethanol. So for example, if we were using sodium hydroxide as our base in alkaline conditions, we would get, from here we've got, what is this? It's ethyl propanoate. Okay, so our ethyl group on the right, our propanoate on the left. So we're going to get ethanol from the ethyl, and we're going to get propanoate from the propanoate part, and we're going to get sodium propanoate, because we're reacting with sodium hydroxide. Okay, the reaction with ammonia in alcoholic conditions, important, is that we get a primary amide and an alcohol. So again here, what are we starting with? We're starting with methyl. This is our methyl propanoate. Propanoate here on the left, this is propanoate, and methyl here. Again, we get an alcohol, which comes from our alkyl group, our methyl in this case, so we get methanol. And we get this part here. Now we actually, so it's a little bit more complex, this part, but we get the methyl takes one of these oxygens, so we're getting the CH3O is becoming the methanol, and the NH, we're adding NH2 to the rest of it. So you can see here we get the same as we've got over here, minus one of these oxygens, with NH2 on it, and that would be propanamide, so it's a primary amide. If we react an ester with an amine, we get a secondary amide. So again, we get from the CH3 and the O, we get our alcohol, plus actually one of the H's from the ethanamine. So we get our alcohol down here. So it's the CH3 and one of the oxygens plus a hydrogen from the from here. gives us methanol. And then what happens is this nitrogen actually bonds to this other oxygen. So we're cutting this molecule here, and we're bonding this nitrogen to this oxygen, which is why over here when you see it written, you'll see that we have this part. So this part here is over here, and then the nitrogen bonds to that oxygen. So we have NH. Remember, nitrogen only forms 3 bonds, so we only have a single hydrogen, not another one. One of these hydrogens ends up in our alcohol. So a single hydrogen and then CH2, CH3. So it's just this same thing here, but the other way around, just flipped backwards. That's all, and bonded to this this oxygen here from the ester. So yeah, just to reiterate, an ester reacting with an amine, we get a secondary amide and an alcohol. Okay, soap making. Glycerol is another name for propan 1,2,3 triol. Let's have a look at a picture of that. So this is glycerol here. It's propan 1,2,3 triol. So a hydroxyl on the first, second, and third carbons. That's glycerol. Fats and oils are triesters of glycerol. What that means is that we're taking glycerol and adding to it to make it into a triester. So we've got basically a triple ester, if you like. So this is just an example of one with 18 carbons attached to it. I don't know the naming of that, but yeah, there's a triester of glycerol. We make soap by conducting the alkaline hydrolysis of triesters of glycerol. And let's look at an example of that. So here is our triester of glycerol. We react it with sodium hydroxide, that's to carry out hydrolysis in alkaline conditions. We get glycerol, and we get sodium stearate, 3 moles of sodium stearate for each mole of our triester of glycerol. Sodium stearate is the most common soap. So we're getting glycerol by cutting off the molecule down here, so splitting between the oxygens, and no, sorry, we're not. We're splitting actually here. We're splitting after that oxygen, and the OH is adding onto the onto this molecule to form to go back to our our glycerol, propan 1,2,3 triol, 1,2,3 propan triol. And what's happening is we're getting these 3 molecules ending in OO are reacting with the Na to produce sodium stearate, which is soap. Okay, so that's Esters. Just to reiterate, long chain carboxylate sodium salts are soaps. And what we did is we started with glycerol, which was this molecule here, propan 1,2,3 triol. We make a triester out of it. So basically it's a triple ester, 3 ester functional groups coming off in a single molecule. Could be longer or shorter carbon chains than this. I think soaps tend to be long chain. We hydrolyze it using an alkaline conditions, which splits the molecule down here. The OH adds on to this molecule to go back to produce our alcohol, which in this case our triol, glycerol, and the sodium joins onto this carboxylate part to form sodium, in this case sodium stearate, which is the most common soap. So it's a carboxylate salt with sodium. Okay, and that's esters.